Good afternoon, everyone. We are going to talk about this paper titled as HalluciDoctor Mitigating Hallucinatory Toxicity in Visual Instruction Data. It was published in CVPR in 2024, and it has 53 citations so far. As you can see on the screen, these are the authors that wrote this paper. So let's talk about the problem statement. So as we already know that MLLMs excel in multimodal understanding and generation tasks, but there is a very big issue that the machine-generated instruction and data contains hallucinations. This is primarily because of the training data that we have that contains hallucinations, so that it cannot be avoided. The goal of the paper is to detect and remove hallucinations, of course, via cross-checking. And to do that, they introduce a two-module framework, which is what they call as HalluciDoctor. This framework addresses spurious correlations. What it means is that in the training data, sometimes due to the sheer number of frequency, the model learns relations between two objects. For example, let's say if fork and spoon appear together a lot of times in the training data, the model will learn that if there is a fork, there must be a spoon. And sometimes that's not the case. So this is not exactly the right thing. Anyways, what they also want to do is that they want to improve the robustness of the existing MLMs by adding counterfactual data expansion. So let's talk about the types of hallucinations. The first type is object hallucinations. As you can see in the image, the correct caption would be a man is sitting on a bench. But let's say a model generates a caption which looks something like a man is sitting on a bench next to a dog. Now, the dog does not exist in the image, so it is just hallucinating an object. That's this kind of hallucination. Now, let's talk about relation hallucination. If you look at this image, the correct caption would look like a spoon is inside the bowl on the table. The hallucinated caption would look something like a cup and a spoon is on the table. Over here, as you can see, that there is incorrect relationship between spoon and bowl, because spoon and bowl are not lying on the table, but they're not lying on the table, but the spoon is inside the bowl. Now let's talk about attribute hallucinations. The correct caption for this image would look something like a red car is parked on the street. The hallucinated caption would look like a blue car is parked on the street. Over here you can see that the attribute, which is the color of the car, is wrong. And so this is attribute hallucination. So standard way of measuring hallucinations is chair matrix. So the standard chair matrix is basically a ratio between non-existent objects and total objects. Now let's talk about paper's extended chair matrix. So the paper introduces chair object, which measures object hallucinations, chair relation, which measures relation hallucinations, and chair attribute, which measures attribute hallucinations. The key takeaway over here would be that higher the chair scores indicate more hallucinations. The formula for chair object would look something like the number of sentences with non-existent object upon total number of sentences. Similarly, for relation, it would be the number of sentences with non-existent relation upon all sentences, and chair attribute would also be similar to the other two. Now let's talk about instance level and sentence level hallucinations. The formulas that we saw before calculated the ratio between the sentences, but there is also another way where you can actually calculate the instance and count the total instances and calculate the ratio. So that's what instance level hallucination is. Basically, it counts each hallucinated element. So let's say the number of times this object is total objects that are hallucinated, and the number of hallucinated objects. That's how you calculate the ratio for instance level hallucination. Whereas in sentence level, you just took the ratio between the sentences as a whole. Now let's talk about Pope matrix, as we have already discussed in the previous paper discussion, and how it compares with the chair matrix. So the problem with Pope matrix is that it has limited hallucination scope, because it only counts the objects objects that are hallucinated, and so it does not understand what contextual errors a passage might contain. Now, it also depends on the object detection, right? Because usually, in most of the cases, we don't have human annotated data, and so the majority of the time people use object detection models, and so there might be a potential bias if you're using an object detection model. The third point is that it has poor attribute evaluation, so there is no way where it can measure attribute hallucination. So that's why chair matrix is better. Now let me talk a little bit about the actual framework and how it works. So this is the first part or the first module, which is the hallucination cross-checking paradigm. And then this is the second part, which is the seesaw-based visual instruction expansion. So this is the part where they add counterfactual examples. We'll go in detail of each step and how the entire framework works, but this is just a general overview so everyone can have an idea. Now let's go step by step what's happening in the actual framework. So the first is hallucination cross-checking paradigm. Now the first step is that look at this image, and then this is the image, and then this is the response. So we have this in our data set, the image response pair. Now what we do is we use a graph algorithm to basically extract these answer chunks over here. These answer chunks are nothing but basically taking two objects and the relation between them. So for example, over here, the answer chunk, the objects over here are people and dining table, and the relation is that people are sitting around the dining table. So just like this, we extract all these answer chunks first. Then we use an LLM to generate questions based on these answer chunks. So if you look at the first question, it would look like, what are the people doing around the dining table? So this is the first step. We generate the questions based on the answer chunks. Then the next step involves, we take this original image and we take these questions and perform VQA task on something that the authors call as MLLM experts, but these are just different MLLMs like Blip2, InstructBlip, and MiniGPT4. Then out of each of these MLLM experts, we get like candidate answers. Now, the next step involves cross-checking. The step is that you take one candidate answer, then compare it with the original response and check the consistency score, which is essentially just a BEM score. Now you do it for all the candidate answers, so you have 3 over here. And then you take the average of that entire score, and then that's how you get the consistency score. Now, what you do with the consistency score, we are going to explain in the later slides. Now I'm going to hand it over to my colleague.
Thank you. So the second part of the framework is seesaw-based visual instruction expansion. So here the main task is actually to increase the data set with a valid counterfactual expansions. The reason is that we might have some prejudice, the model might have some prejudice with the hallucinating object where, there might be co-occurring objects, and this might further increase the hallucination effect. And to avoid such issue, we might need to look at the data itself and add some valid examples that we haven't seen, the model hasn't seen before. So the way we do is this. First, coming from the previous step of the framework, we check whether the threshold is satisfied based on the score. If it is not, if it is below the threshold, then we denote this item as hallucinated item. Here, in this case, clock is below the threshold, so that's why we identified as an hallucinated object. Then the second part of the framework is adding counterfactual examples. So the way we do is we select some representative image of this hallucinatory object. Here it is clock, and what we do is we put a bounding box for this object such that later on we can add this clock image to our target scenes later on. The way we select target scenes is this. We will calculate 2 scores, enhancement factor and inhibiting factor. The mathematical explanation, detail of these factors will be explained in the further slides. And based on these scores, for each of the objects appearing in our data set, we calculate a seesaw score. Okay? And the one with the highest seesaw score is selected here as cat, and we go to these target scenes where we see cat. Okay? Here there is a cat, so we need to modify the scenes that contains cat actually. So how we do is this: we get the object from the itself, modify our image by adding this hallucinating object, okay? And then we also modify the caption as there is also a clock in the image, so that we can improve maybe the hallucinating effect of, cat and clock in the further steps. This is actually image level visual instruction expansion. We also have instruction level hallucination elimination, which is done actually at the previous step, at the cross-checking paradigm. Here, actually people are sitting, but the caption says there's a clock placed in the background, but actually not. This was actually the first part of the framework. Now, at the second stage, what we do is we add an image to our target scenes and modify our captions so that we can further reduce hallucinations. So to calculate and decide on our target scenes, we need to calculate seesaw score, and it includes two factors: enhancement factor, EI, to select the rare objects that we haven't seen, the model hasn't seen so far, and also the second factor is inhibiting factor, I, to understand whether this object that we are going to select as our target scenes is a reasonable combination with our hallucinating object. Okay, so here the task is calculating actually a seesaw score, which is actually the multiplication of enhancement factor and inhibiting factor. So let's first explain the enhancement factor. Okay, so here the task is increase the weight of other objects OI appearing in our data set that rarely occur with our hallucinating object O. Okay, so the formula is like this. Here N star denotes the frequency of hallucinating object O, and it's mostly occurring pair O star. Okay, and maximum of Ni, where Ni and 1 will actually give us the frequency between other objects and the frequency between other objects OI and hallucinated object. Okay, and this will give actually a ratio. We do not want to go below 1. The reason is that we want to avoid vanishing effects. So that's why we limit with 1. So here, the example is, let's say we selected our hallucinated object as car, and the most frequently appearing object with car is road. Okay? We want to introduce, at this stage, roads with other objects OI that rarely associated. So let's say in our data set, we have seen road and car occur together 1,000 times. 1,000 times. Okay? So due to the reason that, road and car are the same thing, we need to divide 1,000 by 1,000 to achieve 1. Now, here for other objects like bicycle, okay, let's assume that we have seen bicycle and car appear together in our data set 10 times. We need to divide this 1,000 O star and O frequency by bicycle and car frequency, which is 1,000 divided by 10 to give 100. And also we apply the same thing for traffic lights. This means that we have seen traffic lights and car 50 times appearing in our set, and our enhancement factor for traffic lights is 20. Now here, the inhibiting factor actually is important. The reason is that enhancement factor is not helpful alone to understand whether this is a reasonable combination or not. So here the task is to suppress the weight of objects in rare combinations with O. So we calculate I inhibiting factor for each object as Mi divided by N star. So we explained N star previously, where Mi is the frequency between other objects and O star. This is actually a probability distribution function. You can think of it this way. So here again, the example is our hallucinated object is car, and our mostly occurring object with car is road. We need to introduce unlikeliness for some rare occurrences. Okay, so here we check our database again and see bicycle and road appeared 15 times. So we put it in on the top and we divide it by the occurrence between car and road. And we apply for each object in our data set. Then what we do is at the end, we calculate some score for each of them by multiplying together. And here in our case, we will select the target scenes that includes traffic lights, and we will include our hallucinating object car to that scenes. So this way, we improve our data set LAVA plus further to LAVA plus plus. So based on these further implementations, we want to stop assuming cars always should include road by introducing some counterfactual examples.
All right, thank you, Arman. I will go through experiment setup and baselines. Their objective is to evaluate HalluciDoctor's impact on hallucination reduction as well as the multi-large language model performance. So they use the mini GPT-4 and plug-all as the baseline model, and they also adopt the LAVA dataset as the baseline dataset, LAVA plus, which is a refined dataset based on the HalluciDoctor, LAVA plus plus, which is extended dataset with a count of actual samples. Also, they adopt the chair metrics for the hallucination evaluation, MME scores for the general performance evaluation, GPT-4, and ORIBER benchmark for the quality and accuracy evaluation. So this is first experimental result about the hallucination evaluation. As I mentioned, they use the mini GPT-4 and plug-all as the baseline model. And they also adopt the chair metrics for the instance level as well as the sentence level evaluation. So you can see the result. Using whole LAVA dataset, generate a lot of hallucination than using LAVA plus, which means HalluciDoctor effectively reduce the hallucination in both level, I mean instance level and the sentence level. Also, you can see LAVA plus performance is better than LAVA plus, which means counterfactual samples contribute to reduce the hallucination well. And also, you can see similar trend with the plug-all result with the mini GPT-4. However, you know, there is an intrinsic trade-off between hallucination and the multi-large language model performance. So, you know, we have to compare hallucination and this performance simultaneously. So they extended their experiment to the MME benchmark to evaluate the general performance. You can see the result. LAVA plus performance is better than LAVA in terms of the perception and cognition, which means HalluciDoctor delete the meaningless information in the training data set while maintaining semantic information. Also, you can see LAVA plus outperform the LAVA plus. This is because data augmentation with counterfactual samples improved the perception and cognition performance. They also did a GPT-4-based evaluation for the detailness and accuracy scores. In this graph, you can see detail score stands for the general performance of the model, and accuracy score is related with the hallucination. So we can say higher accuracy score stands for the lower hallucination. So you can see the first result. Using whole LAVA dataset can generate a very detailed sentence, but there are a lot of hallucination in the sentence. And also using other model like LRV can reduce a lot of hallucinations, so you can see this trend. But this model showed the tendency, you know, they oversimplify the generated sentence. On the other hand, LAVA plus can not only maintain the detailness but also increase the accuracy score. Finally, LAVA plus achieved the highest score as well as highest detailness score as well as the accuracy score. However, you know, AI model like a GPT can make a lot of mistakes sometimes. So they extended their experiment to the OR-EVA benchmark, which is human-related evaluation, which means once model generates the sentence, human manually evaluate quality and accuracy score. So you can see the graph. Y-axis stands for the quality score, and x-axis stands for the accuracy score, and also they use the mini GPT-4. As you can see, Lava Plus and Lava Plus Plus outperform the Lava in terms of the quality score and the accuracy score. And this is experimental result on the M-plug-O result. So you can see this graph shows a similar trend with previous one. And finally, they also did the ablation study to evaluate impact of both factor, I mean the enhancement factor and inhibition factor. You can see they used the chair score for the hallucination evaluation and MME score for the general performance evaluation. You can and red bar stands for the without HalluciDoctor, and orange bar stands for the HalluciDoctor without enhancement factor, and yellow bar stands for the HalluciDoctor without inhibition factor, and this is total HalluciDoctor. You can see both factors impact on the hallucination as well as the general performance. So you can see using total HalluciDoctor achieved the lowest hallucination score as well as the highest general performance. You can see the same trend in this graph as well. So based on the result, we can say HalluciDoctor's key benefit can be summarized as, HalluciDoctor can reduce the hallucination, and they also enhance the LLM performance robustness against adversarial challenges, and they also improve the perception, cognition, and factual accuracy. So we can summarize HalluciDoctor